So, last lecture we started studying cyclotomic fields and I stated a theorem. We proved about half of this. So, let me recall that theorem and today we will try to finish the proof of this. So, P is a prime number, okay, zeta p to the r, this is primitive p to the rth root of 1, p to the rth root of 1, and k p to the r, this is q zeta p to the r. Then we said that degree of k p to the r over k is p to the r minus 1 into p minus 1. 1 zeta p to the r and so on up to zeta p to the r to the p to the r minus 1 into p minus 1 minus 1. This forms an integral basis of kp to the r, which means that kp to the r is the ring of integers of kp to the r is generated by this over z. 3 if m is equal to p to the r minus 1 into pr minus r minus 1, then the discriminant of kp to the r is p plus minus p to the m, and sign is minus 1 if p is congruent to 3 mod 4 or p to the r is equal to 4 and it is 1 otherwise. So, that is what we said last time. There were a few more parts. The fourth part said something like the only roots of unity, the only roots of 1 in k p to the r are plus minus zeta p to the r to the s, where s is between these numbers, and 5 was p is the only ramified prime, p is the only ramified prime in kp to the r, and p ok p to the r, this is in fact minus 1 minus zeta p to the r to the power p to the r minus 1 into p minus 1. So, p is totally ramified, not only that it is ramified, but it is totally ramified. And sixth part was Galois group of q, Galois group of k p to the r over q, this is isomorphic to z mod p to the r z cross. Okay. And in fact, this goes to an element sigma a. What does sigma a do to zeta p to the r? It sends it to its 8th power. So, this is the map. Okay. And what did we prove? So, last time we proved the following. So, last time we proved a bunch of things. So, we took psi p to the r of x to be x to the p to the r minus 1 divided by x to the p to the r minus 1 minus 1. So, in particular, degree of psi p to the r is p to the r minus 1 into p minus 1, right. And we proved that k p to the r is the splitting field, of psi p to the r x equal to 0. Okay. Not only that, we proved that psi p to the r of 1 is p, and this is also equal to product s going from 0 to p to the r minus 1, p does not divide as 1 minus zeta p to the r to the power s. Hence, as ideals, we proved that the ideal generated by p is same as the ideal generated by 1 minus zeta p to the r to the power p to the r minus 1 into p minus 1. Okay. So, this thing gave us that the degree of k p to the r is less than or equal to p to the r minus 1 into p minus 1, and this thing gives us that degree of p to the r over q is greater than or equal to p to the r minus 1 into p minus 1, right. So, combining this together we get the following. Hence, so this is where we stopped. Hence, k p to the r over q, this degree is precisely p to the r minus 1 into p minus 1, and as a corollary we get that psi p to the r of x is irreducible over q. So, you may have seen a different proof of this fact that psi p to the r x is irreducible over q, because by using Eisenstein criteria, for example, right, and that would give you another proof of this the fact that degree of k p to the r over q is p to the r minus 1 into p minus 1, but here we use some number theory, some algebraic number theory to get it. Okay. So, hence we get the following. So, therefore, 1 minus zeta p to the r is a prime ideal of OK p to the r, okay, and p is totally ramified in k p to the r, right. So, we got these two things pretty much for free, right, out of our proof. So, that is an advantage of doing it using algebraic number theory. If we used Eisenstein criteria to show that psi p to the r x is irreducible over q, we would still need to show this, right. And so, so I think this is a better way of doing things if we know some algebraic number theory. Okay. So, now we consider the last part. So, yeah. So, so you see that k p to the r is q zeta p to the r, right. So, any automorphism of k p to the r maps zeta p to the r to another, possibly another root of psi p to the r x equal to 0. Right. This is an irreducible, well, I am not right now, I am not using that it is an irreducible polynomial. So, any automorphism sigma in Galois group of k p to the r over q is of the form sigma equal to sigma a, where sigma a of zeta p to the r is zeta p to the r to the power a, right. And so, we get a map, a group homomorphism. So, let me say group homomorphism, then we get a group homomorphism from Galois group of k p to the r over q into z mod p to the r z cross, right. So, here a and P, GCD of A and P is 1. Right, otherwise it is not a root of psi, that is the problem if P divides A. Okay. So, this homomorphism is clearly injective, and up to this point it works for any field. Okay. But now we know that the number of elements in Galois group of K p to the r over Q is equal to the degree of K p to the r over Q, which is p to the r minus 1 into p minus 1, and the number of elements in Z mod p to the r Z cross is also p to the r minus 1 into p minus 1. Okay. Hence, the homomorphism Galois group of K p to the r over Q into Z mod p to the r Z cross is an isomorphism. Right. So, this was the last part of the theorem. We still have to prove a few more parts, but this is the last part of the theorem. So, we are not proving it sort of one by one or in the right order anyway. Okay. Fine. So, next what we do is we find what the next what we do is we find the discriminant. So, next we find the discriminant dkp to the r. Okay. All right. So, how do we find the discriminant? Well, we take a So, what is the discriminant? So, up to sign the discriminant is norm from K p to the r over Q psi p to the r prime zeta p to the r. Right. This is up to sign, the discriminant is this. So, we find what psi prime of zeta p to the r is, and what is this? This is right. So, this becomes how do I write this? This is so one way to write this would be product over all A in Z mod p to the r Z cross A is not equal to 1 zeta p to the r minus zeta p to the r to the A, right, because remember what is psi p to the r of x? This is product A in Z mod p to the r Z cross x minus zeta p to the r to the A, right. So, if I take the derivative and apply product rule, I will get a sum of some products, and if I plug x equal to zeta p to the r, the only term that will remain out of that sum is the one corresponding to taking the derivative of x minus zeta p to the r, and in that case I will just get zeta p to the r minus zeta p to the r to the A for A not equal to 1. Okay. And here is a small exercise, if you like, that you can do. This is precisely p to the r into zeta p to the r p to the r minus 1 divided by zeta p to the r into p to the r minus 1 minus 1. All right. So, this is a small exercise that you can do. It's just an explicit computation. Next, what we do, I mean, yeah. So, so I want to find norm of these things, right? So I want to find. So we want to find norm of this quantity. So we want to find norm from k p to the r over q of p to the r zeta p to the r minus 1 divided by 1 minus zeta, did I write 1 there? Yeah, no. Yes, divided by zeta p to the r minus 1 minus 1. Okay, so so if you look at norm k p to the r over q of p to the r, then this is simply p to the r whole to the power p to the r minus 1 into p minus 1, and norm k p to the r over q of zeta p to the r to the power p to the r minus 1. This thing simply is this thing is simply 1, right, because I mean this is 1 to the power p to the r minus 1. You can make even more precise statement, and then norm of k p to the r over q zeta p to the r minus 1 minus 1. You see, this is I mean this thing is same as norm from k p over q of zeta p minus 1 to the power yeah, okay, maybe let me write it in 2 steps. This thing, because this quantity zeta p to the r, if you raise it to pth power, you get zeta p to the r minus 1 and so on. So this is same as this, and so this thing is norm from k p over q zeta p minus 1 to the power p to the r minus 1, because the degree. So this is because degree of k p to the r over k p, this is p to the r minus 1. Okay, and therefore we get that norm from k p to the r over q zeta p to the r minus 1. This is up to sign, this is p to the r minus 1, right. And so if you put all this thing together, you get that delta squared of 1 zeta p to the r and so on zeta p to the r minus 1, zeta p to the r to the power p to the r minus 1 into p minus 1 minus 1. This is equal to plus minus p to the m, right. Remember m was, so recall that m was this quantity p to the r minus 1 into p r minus 1. Okay. And so how do we find the sign of this now? So how do we find sign? Well, we still haven't proven that this is the integral basis, but okay, let me prove that first and then we go to the sign. Okay, so d k p to the r is equal, or this times some square is delta squared 1 zeta p to the r and so on zeta p to the r p to the r minus 1 into p minus 1 minus 1, right, for some m in the natural numbers, right. So, we want to show that m is 1 and m is a power of p, right, because delta squared of this quantity is also a power of p, which means then that so this, what does this mean? This means that 1 by m z zeta p to the r is contained in OK p to the r is contained in z zeta p to the r. So, the only denominators that can occur are powers of p, right. So, what we can do is yeah. So, now remember, so you observe, notice that k p to the r. So, this is another trick that you learn here. Instead of looking at this, you can look at 1 minus zeta p to the r, right. It is the same thing. And so, you write alpha in O k p to the r as alpha equals summation a n 1 minus zeta p to the r to the power n, n going from 0 to p to the r minus 1 into p minus 1 minus 1. Okay. And where do these a_n's live? This live in 1 over some power of p times z, possibly, right. But you see that if a_n's have a if a_n has a denominator, has a non-trivial denominator for any n, then the valuation of a_n is yeah, what kind of, we are using the multiplicative valuation. So, this is less than or equal to valuation of p, right. But you see that valuation of alpha is yeah, okay, let me put it like this, let me not bother myself with valuation. So, okay, or even if I am writing it in terms of valuation, let me say the following: valuation of 1 minus zeta p to the r to the power n, right. The power of p that occurs here is less than the power of p, yeah, the power of the power of 1 minus zeta to the n that occurs here for all 0 less than or equal to n less than or equal to p to the r minus 1 into p minus 1 minus 1. Okay. And so, if this happens, then the valuation of alpha will be less than 0. This is a contradiction, right. Hence, all these a_n's are in fact in z. So, hence m is equal to 1 and dk is equal to, up to sign, it is equal to delta squared 1 z, sorry, yeah, I will write it like this, up to sign it is simply p to the power m, right. So, how do we determine the sign now? So, how do we determine the sign? So, recall that sine, we proved this a long time ago, sine of dk p to the r is minus 1 to the power r2, where R2 is the number of pairs of complex embeddings. Complex embedding, which is also equal to the number of complex places, right. And yeah, so let us take p equal to 2 first, right. So, r is equal to 1, then r2 is equal to 0, r is equal to 2, then you are looking at 4th root of 1, then r2 is equal to 1, right. And if r is bigger than or equal to 3, then r2 is p to the r minus 1 by by p, this is like 2 to the r minus 2, right. And so so what is the sign here? I mean the sign here is plus, the sign here is minus, and then the sign here are all pluses, right. What about p bigger than 2? Well, whatever r is, r2 will always be p to the r minus 1 into p minus 1 by 2, right. And this is odd if and only if p is congruent to 3 mod 4. Right. So, we have determined the sign as well. Okay. All right. So, yeah. So hence we have hence p is the only prime that ramifies in kp to the r, right, and it totally ramifies as we saw earlier. Okay. So, the only thing that remains to be determined now is what are the roots of unity inside kp to the r. So, let zeta n belong to kp to the r, kp to the r for some n inside natural numbers. Then what we have is q zeta n is contained in kp to the r, right. So, in particular, if L is a prime dividing n, then q zeta L is contained in kp to the r, right. So, if I want to draw a picture, it will be something like this, right, kp to the r and then q zeta L here, and then it is contained in here, right. But I know that the only prime that ramifies in, okay. So, L is the only prime that ramifies in q zeta L, okay. So, L better be equal to, so hence L is equal to P, right. Hence n is a power of P, right. So, hence L is equal to P, or q zeta L is equal to Q, right. In this case L is equal to 2. So, hence n is a power of P or 2 times power of P, hence n is P to the r or 2 times P to the r, right. That is the only possibility. So, plus minus zeta P to the r are the only roots of 1 inside kp to the r. Okay, so we have determined the discriminant, we have determined which primes ramify, and we have also determined what the ring of integers is, right. Now, of course, one can ask what can one say about class number or ideal class group of q zeta p to the n, or more generally q zeta n, and that is generally a very hard question. There are lots of very deep results about it, mainly covered under Iwasawa theory, and there are lots of deep conjectures about it as well. For example, what is called the Van der Waals conjecture. Okay. So, it is still an area that can be explored for research problems, and there are many deep theorems still to be proven in this area. So, next time we will look at computations of ideal class group, not of the cyclotomic fields, but in other examples. Thank you.